Good morning or good evening, wherever you are. We are very pleased to have you in this Human Factors session. My name is Sandy Lozito, and I am the Chief of the Aviation Systems Division at NASA Ames Research Center in California. I'm really pleased to be here. So I want to move quickly so that we have ample time. I'm going to go ahead and introduce our first speaker. Dominic Janish is an R&D engineer in air traffic management at CRETA, working on the development of the CESAR U-Space program and researching the human factors implications of U-Space on tower control as a PhD candidate at TU Delft. Dominic, over to you and welcome.
Thank you, Sandy. Thank you very much for the introduction. Also, thank you everyone for attending this session. Over the next 30 minutes, I would like to introduce the work that we performed at TU Delft on the development of a collaborative interface for UAV traffic management. From now on, I will refer to it as UTM for short, and tower control, in order to establish a future collaborative environment between the two systems. Before I go into the details, I would just like to briefly introduce the rest of the team, which was fundamental in making sure that we got everything on track. So in particular, I would like to extend my gratitude towards Dan van Aken, who was a master's student who supported me in the development of this initial interface. And essentially without him, all of the programming work and setting up the experiments with tower control participants wouldn't have been possible. So I would really like to thank him for all of his work, as well as Clark Borst, who is my academic supervisor at TU Delft, who was making sure that we were on track and that everything worked as according to plan. So before I go into the details of what we were performing to make this initial display work, I would like to face you off or start you off with sort of a vision for the future that we are trying to implement. Now, this is an image that I'm going to show you is not our own. It is courtesy of Airbus, but it is a vision that is shared across the industry in the development of new modes of transport within our urban cities and within lower airspace. What you can see here are operations of massive amounts of UAVs, which can be either carrying passengers or transporting goods, as well as performing other relatively important tasks within lower level airspace within urban centers, such as also transporting goods, overseeing high risk areas, or also performing routine inspections of buildings, of streets, of pipelines, and so on. Now, industry efforts over the last few years have been quietly intensifying on the development of a system to manage all of these vehicles, which is the so-called UTM system, or in Europe as it is called U-Space. Now, as you can imagine, this is an ATM session. So, and in particular, human factors, you might ask yourselves, well, what does the human actor have to do with this? Well, if you introduce so many types of vehicles and such a new paradigm into urban centers, for instance, this will, of course, inevitably come at odds with the existing air traffic control system, which is very much still in control over the airspace around our cities. I would like to exemplify this a bit further by providing this sort of high-level example. This is the northern part of the city of Rotterdam. And if we sort of superimpose some of these UAV missions in a schematical way, operating in the vicinity and within the city, you can see all of these vehicles performing relatively mundane but potentially important tasks, such as inspection of highways or the inspection of the Rotterdam harbor, which is a really important harbor in the Netherlands, as well as the transport of goods between hospitals from one part of the city to another, all of which are overseen by this very autonomous and highly automated UTM system. Due to the complexity of the missions, it is not feasible to have human actors within this system coordinating UAV vehicles. Now, that in and of itself would be fine. There wouldn't be any type of issue. However, as you can probably already notice, you also would have to deal with manned aviation, which is operating within the same area, within the same airspace. This is, of course, a very legacy system. Air traffic control is mostly manual and human-centric. So you would sort of have a clash of two types of concepts coming into this future development, which would be, on the one hand, the UTM system, which is highly autonomous and uses levels of automation and autonomy to make sure that all of these types of missions will be coordinated. And you have air traffic control, which is very much limited by the capacity of the human actor, of the tower controller in this particular airport example, to be able to manage manned aircraft. So what we were asking ourselves is, well, what what could we provide the human actor with in this sort of future environment that they can, on the one hand, understand what this UTM system is performing on their traffic and still perform their mostly manual tasks related to managing manned aircraft. So we wanted to go about and understand any type of interface design considerations to help the human actor within such a collaborative environment. In particular, this is our first study into this, this domain, and we wanted to focus it on understanding two things. What interface requirements would the human controller need to be able to monitor UTM actions, as well as guide these types of UTM actions if necessary? No system is perfect. UTM is also not expected to be a perfect system, so there might be room for conflict. So in order to do that, we did a sort of two-step approach. First, of course, we needed to understand the problem. So we did quite an extensive review of existing literature, and particularly focusing on the UTM domain. We had a look at the American side, the FAA LANS concept of operations, as well as the U-Space concept of operations, which has been developed over the last few years, as well as accompanying research. Moreover, in Europe, the system is now also turned into a regulation. Back then, at the time that we were making this study, was still an opinion, but we used that as an input to make sure that our assumptions on the UTM system are valid. And we wanted to support this with also future developments in air traffic management and the progression of more and more autonomy into UAVs to really understand how the operating environment would look like. We then supported this with interviews with actual aerodrome tower controllers situated in Rotterdam to understand their own needs for managing airport traffic and how the tower control environment looks like nowadays, to get an understanding of what kind of interface they would actually require in order to be able to understand what the system is doing. I would like to briefly now introduce some of the most fundamental points of this interface that we came to our conclusions by doing this, this literature study. What you're seeing here is sort of a mock-up ground radar display where you can see some of the more common elements that we're used to already in air traffic control, such as the indication of manned aircrafts utilizing blips, as well as an indication of the runway at Rotterdam The Hague Airport, a very schematic representation thereof. Flight strips which portray the most relevant information for this initial display that we wanted to develop. But of course, you can also see some novel elements, which I would like to briefly introduce now over the next few minutes. First and foremost, of course, the role of a tower controller is to also is strongly supported by their means to visually identify the traffic that they're managing. For UAVs, we just saw that the small size and the large quantities of these vehicles would just not make it feasible for the human actor to visually see them. So it was important for us to include references of these vehicles into the display. In this case, we also wanted to play around a bit with identifying two different types of vehicles, either fixed wing or multi-rotor vehicles, which have different behavior depending on the flight parameters of the vehicle. Moreover, we thought it was necessary to give the human actor an understanding of where these vehicles aim to go. So not just localizing them, but also understanding what their mission is if they want to. So we provide the interface also with an indication of being able to select the intended routing of the UAV, which would be available through the mission planification of that vehicle, and to portray that routing on the display itself. What you're seeing here is also some additional information that we wanted to test whether this would have an impact on the human actor in terms of their decision making. What you're seeing here is this oval shape. This can be any type of arbitrary shape, but what we wanted to indicate with this was an indication of UAV mission constraints. This is because, in particular, in UTM operations, we will have very small vehicles which will likely be very constrained to a particular operating environment due to risk hazards or areas which they're not allowed to fly. And this may inhibit them to maneuver according to the manned aircraft traffic situation at the airport. So we wanted to sort of highlight this in a more graphical sense to see if this is an information that tower controllers would be interested in knowing. So UAV mission constraints are highlighted using this surface plot. This is now an important element that I want to highlight as well. Maintaining safety within the airspace. You can expect the UTM system to be quite automated, but there needs to be some means for the human actor to also reinforce safety issues. What you're seeing here is an activation of several cells of this sort of grid that you've seen in this layout. Well, what is being activated here is a so-called geofence. This is a structure, a very intimate or integrate component of the UTM system, which allows the system to block specific regions of airspace virtually for UAV travel. We wanted to give this ability to the tower controller as well in order to reserve particular airspace and clear it essentially from UAV traffic, in order to perform their own separation actions if they deem that necessary. In this case, you have seen this UAV would now reroute around these areas, and the conflict with the arriving air traffic would be mitigated. Something that you might have also noticed when I was switching slides is that the smaller surface plots also shrank. This is another indication that we added to this interface, which was an indication of the available UAV endurance, given that these vehicles are expected to have a very low level of endurance due to the increasing shift towards battery-powered vehicles. This is something that it might be necessary to understand that the limitations of autonomy of these vehicles are much lower than they would be in traditional commercial aviation, where we're talking about the span of at least, for instance, 45 minutes of fuel reserve at the end of a trip, which for the UAVs might not be possible. So any type of rerouting action performed by the controller might have an impact on the UAV endurance. Now, similarly, we have another situation here with another UAV, which the controller would then activate these geofences as well to maintain safety if necessary. Now, we wanted to add one more indication to this display that we wanted to test, and that is the differentiation between levels of priority within UAVs. In particular, here we have two types. One is a red UAV and the other one is a blue one. We gave the red color to the higher priority UAV. You can imagine, for instance, an emergency flight between hospitals. So this would be a use case which would have a higher priority of one UAV than another. And we wanted to understand whether the controller would actually use this information to, for instance, increase the efficiency of specific UAVs so that they can continue along their path in a much straighter line. So these were the interface considerations that we came up with and that we wanted to test. Of course, now we needed to put this mock-up into an actual simulation environment, which we did. What you can see here is the simulating environments, the sort of initial design mock-up that we performed to test some of these interface elements. This was, of course, based on this conceptual design study that I just presented. The underlying automation of vehicles that they would reroute around particular areas was, of course, simulated using an A-star path planning algorithm. We wanted to use that to simulate UTM system actions. It's not as sophisticated as it potentially could be, but for the purposes of this initial display, we thought it was more than adequate. And to sort of provide some more insights into how this works, I would like to direct you to this website. We've made the simulation platform available for free use, so you can actually play around with it and get a better understanding of what these interface elements do and how they would work in a more dynamic setting. So feel free to access this link, and we'll also put it up at the end of the presentation, so you can have a look at it for yourself. So this was the setup. Now we just wanted to test it with some volunteers. However, we had a problem. COVID-19 happened. So we couldn't do this in a typical human factors session where you would have people come to a particular setup and they would sit there and you would be able to analyze them and ask questions. So we had to be a bit creative, and we shifted the entire simulation platform online to a browser-based simulation. That's also why you can use this link to access it. And we coordinated the entire human factors simulation using Zoom. So basically what we're doing right now, but in terms of an actual human factors experiment. This has, of course, a lot of limitations, but we thought, or we weighed out the limitations with the benefits of potentially getting more participants due to the fact that we could do this online, and the fact that this was just an initial design study. We thought it was definitely worthwhile to give it a try and coordinate this via Zoom. The participants that we then gathered were tasked with 4 scenarios that they would need to master. The first one was a scenario where we had conflicts of UAVs with typical IFR traffic at Rotterdam Airport, in this case, following the standard instrument departure and standard arrival routes for the airport. And we had a sort of Boeing 737 type aircraft modeled in this simulation. The second one, which was a bit more interesting due to the lower operating altitudes and the much less predictable maneuvers of vehicles, was that of a visual flight rules traffic scenario. So we had a aircraft which were more or less the followed more or less the pattern of a Cessna 172 type aircraft on the approach or the visual approach paths for the airport, and had conflicts with UAVs simulated. Then another really important scenario for us was the inclusion of emergency helicopter flights, as we thought that the low operating altitudes of these helicopters, which usually have to depart in quite a hurry, they have at a maximum 2 minutes of lead time before they usually take off at Rotterdam Airport into more or less random directions. We thought that this was a really interesting scenario to have a look at, because it would clash directly with the low operating altitudes of UAVs. And then finally, we had one scenario which mixed all of the previous scenarios together into one to generate a higher task load. Although workload and situation awareness was not the full ambition of this study, we did want to see if the inclusion of all of these scenarios, if we could get some initial results in terms of workload and situational awareness from the participants, to see if increasing the amount of UAVs and increasing the complexity, or what effect that would have on these participants using this interface. So we then needed to get a hold of participants. We managed to get 9 air traffic control professionals to attend as volunteers in the study. They were from both the Netherlands and Spain, 5 of which were active tower controllers. Then we had 2 controllers which were en route controllers but had a tower control rating, and we had 2 former tower controllers as well participating in the study. And they were tasked with essentially performing 2 things. The first was to ensure vertical and horizontal separation of UAVs from manned aircraft in the scenario, and the second one was to minimize any additional UAV travel time that their actions would inhibit on the UAVs operating in their airspace. How would they do this? We were only giving them a single tool, because that's the tool that we wanted to test, and that is the utilization of geofences or a grid of geofences to perform any type of traffic deconfliction actions. We gave them we tested 2 geofence sizes, a larger 1x1 nautical mile grid resolution, because this was a bit more intuitive to the types of distances that tower controllers are used to, and a much finer 1x1 square kilometer grid, which would be more efficient towards UAV missions. And what is it that we actually wanted to measure? We wanted to find out 3 things. First, what the control strategy was using this type of a setup. Then what the control behavior of the controllers were in the utilization of geofences. And then finally, what interface elements that I just previously introduced, how useful were they in the performance of these tasks? So we performed these experiments remotely, and these were the results that we've gathered. Beginning with the control strategy, we found that the control strategy didn't vary particularly from what the typical control strategy in tower control would be, which was to a certain degree surprising, but also something that was expected. And just to reiterate what that control strategy typically is that first you obtain situation awareness. What the participants did was they checked first what the UAV intents were, then they checked what the intents of the manned aircraft were, and scanned for potential conflicts. Then if a conflict was found, the idea was, of course, to resolve this conflict utilizing geofences for these UAVs to reroute themselves around manned aircraft. And the strategy typically in air traffic control is to resolve any pending conflict as soon as possible, given that the longer you spend time on having to analyze a particular conflict, the more resources you use up and the more room for any other type of error you allow to occur as part of this during the resolution of this one conflict. So this was really priority for controllers to resolve as soon as they could. And only after the conflicts were resolved did they pay attention into increasing UAV efficiency if necessary. They would do that by tweaking particular geofences to allow UAVs to travel in a more direct route. Now, from this strategy, we didn't really see any type of, this was nothing out of the ordinary. This is something that we had expected. However, what we did find very surprising was the very active nature that tower controllers wanted to use on the UAVs. In particular, they wanted to apply the same sort of vectoring strategy that is used in tower control or in control in general on this UAV traffic within the traffic region. And this caused a series of problems, which I would like to now go into a bit further when I'm talking about the control behavior. So we found that participants would either fall back to one of two strategies. The first one was to aim to protect manned aircraft using geofences. This is something that we had expected. You can see here in this image a helicopter departing to the southwest, which is just being blocked or reserved areas with geofences to stop all UAVs from entering there and just to give it a clear path to fly into this direction. This is sort of the control behavior that we expected for all of the flights. However, given that controllers had a very active interest in vectoring individual UAVs, we found situations that, as the one I'm presenting here on the right, you can see an aircraft on final approach to the runway, and there are some UAVs operating in the vicinity. The controller wanted both UAVs to cross, but this UAV would need to cross before, and this UAV would need to cross after this approaching traffic, essentially following the typical strategy of vectoring a slower aircraft behind a faster one. And what they utilized was actually they were activating geofences, which were just activated due to the sole purpose of having to redirect vehicles around the geofence. So this geofence that you can see here is actually not protecting any type of airspace or manned aircraft. It just serves the function of rerouting a particular UAV. However, this is not really how geofences are designed to work, and the complications then also were that the activation of particular geofences would of course also affect the routing of all the other UAVs which aim to go through the same area. So this would actually cause conflicts when resolving another conflict. So this was a major limitation that we found for the utilization of geofences for this purpose. Now, going into the last point that we wanted to find out, the interface usage. These were the results from the post hoc questionnaires that we gave the participants in terms of the utility of the elements that they were provided with. We found that elements regarding maintaining separation, so basically achieving the high-level goal of safety, scored highest. This was in particular the indication of the UAV routing and the activation and deactivation of geofences. What we also found interesting is a high level of utility assigned to the UAV priority. I'm going to go into that a bit more in the discussions, but essentially this also means that controllers had an active interest in the level of priority of UAVs within the UTM environment. So this was an interesting result as well. Then elements regarding the efficiency of vehicles scored a bit lower. This was also sort of supported by the strategy that we observed that the efficiency would then become, would be last. So the indications were not really actively considered when a conflict was found, but the controllers did mention that when they did consider UAV efficiency, the indications of range and mission parameters were useful in them to understand what they could do to help these UAVs pass more efficiently. And then finally, all the labels which are, or all the elements which were relevant to manned aircraft scored lowest. This was mostly due to the fact that the controllers were not actively tasked with controlling manned aviation, and therefore also didn't give them too much attention. So these were the main results. Now, coming back to the sort of initial question that we gave ourselves for this initial study, what interface would the controllers require to monitor and guide UTM control actions? Well, in terms of monitoring, we found, of course, that the interface elements which help them achieve their high-level strategy of safety first and then efficiency, everything that was related to safety, such as localization and locomotion indications of the vehicles, as well as their priority, was considered very relevant. Elements which were related to the UAV endurance and mission parameters of the UAV, so linking themselves to efficiency, scored lower, but were still considered. In terms of being able to guide UAVs, the arrangement of geofences in a grid was very well received. So the controllers were very happy about the facility of just being able to activate certain areas if they wanted to. And they found it was very useful in maintaining separation from the manned air traffic. In terms of geofence sizing, we found that ATCOs preferred larger ones than smaller ones. And this is where we come back to the UAV priority color. This is really an insight that I wanted to share with you as well, is that controllers were actively interested in giving certain UAVs priority over manned aircraft. Now, this is also something that we weren't expecting. We were expecting them to just sort of give priority to what their own traffic was and sort of set aside the UAV traffic. But they mentioned that in particular cases, if they had a high priority UAV, they would have actually liked to be able to instruct a VFR traffic to orbit and let the UAV pass rather than the other way around and giving priority to the traffic which has a human on board. So this was a really interesting feedback that we sort of unanimously received from all of the participants, and I really wanted to highlight this also in this section. Of course, the elephant in the room for us was that the UTM control actions using geofence did not always correspond to the intentions of the air traffic controllers, in particular when they wanted to vector UAVs. This also showed that they did have an interest in being able to actively tell individual vehicles to either perform a different type of maneuver rather than having to activate an area which affects all vehicles in the area. Now, there is one very big consideration or limitation of the results that I'm presenting. And this is, of course, as you've already noticed, that this was a design study which is mostly focused on the UAV part. There was no control over manned aircraft. So ATCOs in this scenario were able to provide their full attention to UAVs and their full attention to the screen that they were presented with. In a more advanced study, of course, we would need to provide a more realistic environment, which would also include allowing them control over manned aircraft. This would likely very much shift their priorities, in particular concerning UAV efficiency. Moreover, controllers spend most of their time looking out of the window. So the face down time is very limited in general. So it would be interesting to also, in a future study, have a look at what this would, what the impact of that would be on this interface that we've designed. And finally, there was no verbal communication work going on either in this initial design study. In the future, of course, this would need to be incorporated and would definitely require a lot more workload from the controller's side and use up a lot more mental resources than they were able to provide in this initial study. However, we did get some very interesting feedback and conclusions, and this we want to take into some of our future work. In particular, we would like to improve the display based on the insights that we've obtained from this initial study. We would also like to focus much more on the control behavior and how it would change in comparison to control of manned aircraft. So really compare the results that we've achieved now, where they were able to provide their full attention to UTM traffic, and shift more towards this sort of collaborative environment to see what aspects will change. Moreover, we would like to incorporate many more mission types of UAVs. For now, they were just point-to-point missions, but in the future, of course, we would also like to incorporate missions which have a fixed routing or are very limited in the rerouting actions that can be performed on them. We would also like to incorporate more sophisticated UTM control actions, as well as varying degrees of automation, which in the end will just come down to the levels of latency between the activation of a particular geofence and the rerouting of the vehicles according to these geofences. The entire aim of this study is then to be able to go towards a more profound assessment of workload and situation awareness by utilizing all of these elements that we've just introduced and seeing how much this would actually help or limit the ability of the tower controller to be able to manage such a complex environment as we're presenting them right now. And what we're performing right now is also cross-checking the findings that we've had with the just recently published U-Space regulation. In particular, the parallels between the utilization of geofences and this concept of dynamic airspace reconfiguration, which is mentioned as part of the U-Space regulation. We find that there are a lot of overlaps, but we still need to look a bit further into where these overlaps are and how can they be utilized to support the development of this dynamic airspace reconfiguration concept. So from my side, that's all I wanted to mention for now. If there are any questions, of course, you can also, that we aren't able to go into in this Q&A session, feel free to write me an email. And also, like I mentioned before, feel free to access the simulation environment at dronectr.tudelft.nl for free. So I think from my side, we can go towards the Q&A.
Thank you very much, Dominic. That was a really interesting presentation. I enjoyed your paper as well. I encourage you all to enter questions into the Q&A. And while we do that, I have a couple questions for you, Dominic.
Sure.
So you noted in your presentation and in your paper that your participants were not required to actively control manned traffic, and that was in fact a limitation of the study. Can you comment on what you might anticipate you may need to change about your design or your procedures should folks be actively monitoring and managing both UAVs and manned traffic?
Yeah, that's a very good question, and that's a big elephant in the room question in general. What we found in particular is that there's a big risk of, we're considering here the future environment that we're trying to develop has a ratio of 10 UAVs for every manned aircraft, right? So at this point in time, the interface that we have provides a blip for each type of vehicle within the airspace. In the future, the risk of having visual clutter and therefore also basically breaking situational awareness by providing too much information is of course there. So there would need to be some future elements that potentially we could rely on automation for that as well, which would only highlight, for instance, relevant conflicts of UAVs, or something that could really minimize and only allow the controller to focus on the conflicts that they are actually interested in. So this is definitely one aspect of this interface which we would need to take a look at. The other one would be also perhaps reducing the amount of information that we provided. We did find that, for instance, controllers did not really consider the UAV endurance as much as we thought they would. So for them, it was really just important to deconflict, and the endurance was sort of up to the UTM system to resolve by itself. So we would actually also reduce perhaps some of these indications that we have on the display.
Thank you, Dominic. Seeing no other questions, I'll continue with mine for this time. Did you ever have a case where your UAV acted in an unpredictable way, either planned or not, or did they always follow their path?
This was relatively regularly that this occurred actually throughout the simulation. We found that in particular when controllers were interested in actively vectoring the UAVs using geofences, that this became an issue. So there were like two elements to this. The first one was because the UAVs were performing their task as they were supposed to. They were being rerouted in the shortest route around the activated geofences. It was just not a route that the controllers expected them to. So this caused, in some cases, more confusion than it actually solved. And this is also one thing that we found that might be a major limitation of this sort of collaborative environment, is that even if controllers provide their full attention to UAVs, as they were able to do in this study, the behavior of the UTM system and the decisions that the system makes may be counterintuitive to what the human controller expects. So developing a means to sort of make these actions transparent, but also in a way that is not intrusive, that's going to be a major challenge, I believe, going forward. So this was from just the nominal operation point of view. Then, of course, we also had some situations where the UAV was not able to reroute itself because it was blocked or couldn't find a way out. This, of course, also caused some confusion from the controllers, and is potentially also something that would need to be looked at into the future. But for the most part, we were very surprised by on the one hand, very proactive way that controllers were interested in making sure that these vehicles go the way they want. And in the end, if it didn't do it the way they were actually wanting them to, it was interesting to observe that. Yeah.
Yeah, that is a surprising finding. I have yet another question for you. Given that your concerns, as you expressed in the paper, about heads down time and things like that with your interface, have you considered using something other than a visual graphical representation? Synthetic voice, speech recognition, other things?
We haven't really gone down that path just yet, because we wanted to see how much we can achieve with just this type of interface. However, there are many things that you could theoretically consider. One way or other studies in terms of human factors are going towards sort of augmented reality. If we're thinking like the development towards remote towers as well, with screens, this could be a potential assistance to be able to identify vehicles which are in conflict with drones, by also sort of highlighting them in the sort of face up time or being able to have some sort of indication on a heads up display. But for now, we really wanted to focus on just this heads down display because I would believe it is also fair to assume that given that we have now time to develop a UTM system which is sophisticated and meets aviation safety standards, I believe much of this work can also just be taken over from the UTM system, and we can sort of hopefully be able to trust automation a bit in a way that the controller would only need to be really interested in UAVs which really present a conflict or a danger to manned aircraft, and for that sort of limits the type of interface that they would require. But definitely, I would say being able to sort of augment reality would be another aspect. Voice is not something that we have looked into, although it is true that this is a very common channel for air traffic control. So there might be some utility there as well, but I wouldn't put my hand in the fire yet to say that it would be useful or not.
Fair enough. And Dominic, we do now have a question. The question is, do you think the tower controller overprotected manned flights via geofencing? If so, do you think having human operators on the UTM side to negotiate may help?
That's a very good question. From what we saw, it was actually less. We were expecting them to be more protective than they actually were. So they were really limiting the utilization of geofences as much as possible, mostly because I believe they considered it also sort of their task to provide efficiency to the other vehicles as well. So this was a really interesting observation as well. We expected them to just sort of block all the airspace and then be done with it, but they were actively interested in maintaining that. So I wouldn't say the geofence utilization was very restrictive or overprotective of manned aircraft. What we also found interesting is that controllers, usually in the tower control environment, they don't consider altitude differences that much. However, for the UAVs, which were operating at a very low altitude, sort of in line with what the industry is developing for very low level flights, they did consider that since it was below VFR operating altitude in many cases, that it wasn't a conflict and they were able to have these vehicles pass relatively close by without the need of activating a geofence. I'm sort of lost the second part of that question. Could you maybe reiterate that?
Yes, and if you could answer very quickly, Dominic, we're over time. However, the second part is, if so, do you think having human operators on the UTM side to negotiate may help?
Very likely, at least for the transition phase, I would see that as perhaps necessary, or at least human operators in terms of having another air traffic control or air traffic management official being tasked with sort of managing this association of geofences or association of airspace towards UTM and manned aviation. I think that would be necessary, at least in the short term. In the long term, when we can hopefully rely on a bit more of sophistication of the system and automation, perhaps this will not be as necessary.
All right, thank you, Dominic. And we are out of time. I think you have one question, but you'll be able to see those later and respond. So thank you again. Excellent presentation, and we will virtually applaud for Dominic. Thank you, Dominic.
Thank you very much.
Yes, thank you. Moving on to our next speaker, equally interesting, I'm sure. Dr. Pallavi Mohan is a research fellow at Saab NTU Joint Lab, Nanyang Technical University in Singapore, and investigates mixed reality systems and interaction design for air traffic control. She completed her PhD in human-computer interaction from Nanyang Technical University in Singapore, where she researched multimodal human-computer interaction designs for virtual reality systems. Pallavi, over to you. Thank you.
All right, thank you, Sandy. Just give me a moment. Can you see my screen now?
Yes, and we can see you. Thank you.
All right, perfect. So hello, everybody. My name is Pallavi, and I am a research fellow at Saab NTU Joint Lab, like Sandy just said, and I come from NTU Singapore. Before I start, I want to take a moment to thank my fellow co-authors, Professor Samir Alam for his guidance, Mohammad Nadir Shah, Osa Svensson from LFV, and Nimrod Lilith for all of their fantastic contributions to this project. I will be presenting our paper titled Embodied Multimodal Interaction with a Portable Mixed Reality-Based Digital Tower. Now, big title, let's see what it's all about. So Our paper, in its very broadest sense, tries to look at how digital towers can transform to exist in the space between the physical and the virtual. In other words, in a mixed reality space. We explore a proof of concept system of this as a very initial step towards this vision. And we also have a preliminary assessment of how effective such a system potentially could be. Now, before we get down to the details, here is a quick overview of what I will be covering today. I'm going to be starting with an overview of this paper and its key contributions, followed by some related work in this field, followed by how mixed reality and ATC come together. I will be talking about our system design as well as our interaction design. And I will also take you through a preliminary assessment we had with some air traffic controllers on our system. And I will finally conclude with a few key outcomes and future plans for our system. So let's start with an introduction. So this paper basically proposes a mixed reality based portable remote digital tower system that has embodied multimodal interaction capabilities. And I'm going to be breaking down this in the next few slides. The paper's key contributions can be summarized as follows. We have partially replicated a digital tower system in a mixed reality environment using Microsoft HoloLens 2 by building a novel 3D simulation system of the out-of-tower view in mixed reality. You can see the headset on the picture right here. We have also incorporated embodied interaction capabilities into this system by defining hand gestures for selective information retrieval by controllers. Thirdly, we have integrated multimodality into this interaction design by leveraging information of the controller's eye gaze to provide spatial context awareness in the mixed reality environment. And finally, the system is preliminarily assessed for acceptance by some experienced air traffic controllers. So ATC towers have come a long way from conventional physical towers to remote digital towers that have dedicated displays at a separate location. Now, such digital towers offer a single shared out-of-tower view, but controllers need to look down at their individual displays for additional information, which goes on to decrease their situation awareness. We know of this as the head down time, HDT, and we have been on an eternal quest to reduce this time. Now, let's consider some recent work that have looked at emerging technologies as a solution for this issue, much like we have. First of all, CESA Retina is a 2018 project that explores using both virtual reality and augmented reality to provide a conformal visual representation of the out-of-tower view along with relevant information. Now, this is a very interesting project created quite early on using very emerging technologies that are actually more mature today than they were in 2018. That is how fast they've been evolving. But this system, while it has been very important, also faces a few challenges that includes increased physical workload and overlaid information clutter on the out-of-tower view, especially in the augmented reality situation where all available information is presented all together on a single screen. Now, there are other digital tower systems out there today that also only have limited interaction support with very basic menu-based interactions, which in turn detract from the out-of-tower view as well. Now, let's look at another work that builds on this concept from Retina. This is a system proposed by Haneol in 2019, and it is a preliminary 4-dimensional mixed reality system. Now, this system uses gestural and voice interaction through Microsoft HoloLens 1, which is an earlier predecessor of Microsoft HoloLens 2 as the world's first mixed reality headset, perhaps, to control both air and ground traffic. However, the interaction capabilities of this system are primarily limited to voice commands for menu-driven input selection. Now, voice-based interaction in ATC systems poses a risk when interacting with an ATC system because controllers use voice as a primary mode of communication with pilots, and any additional interaction that requires voice as a primary input modality can potentially interfere with this critical communication channel. So when we try to address the issues that I have been talking about, we leave voice out of the options of interaction because of this challenge. So after a thorough study of available literature on digital tower systems on various platforms, we summarize a few key repeated issues here. Firstly, platforms such as virtual reality largely offer limited field of view and visualization options, since such devices are not generally geared towards safety critical operations such as air traffic control. They mainly belong in the entertainment and gaming industries. Secondly, the less head down time, the better always. But this should not come with some associated drawbacks we've seen, such as visual clutter, which is the third issue, where all available information is overlaid altogether simultaneously onto a single view. Another key issue is the lack of intuitive interaction methods. The available interaction methods with present-day digital tower systems are mostly point and click based or voice based, like we've seen. Now, this brings us to a pertinent question. How can we develop a system that addresses such challenges while also removing the need for massive spatial displays altogether? The answer might lie in mixed reality, but that might not be all there is. Mixed reality offers a blend of physical and digital worlds that unlocks natural and intuitive human, computer, and environment interactions. But when it comes to adopting new platforms like this for a critical environment such as ATC, we have to ask ourselves, how do we alleviate the unfamiliarity for controllers to adopt to new interfaces to perform very intensive cognitive tasks like they do day to day? Now, it has been studied that immersive visualizations of air traffic increase situation awareness. But such immersion cuts the controller out from the outside world and limits their collaboration. But mixed reality headsets, or mixed reality in general, however, supports a see-through immersion model. In such an air traffic system, you get an immersive view of the runway with integrated data overlays while you still maintain your view of the outside world. So this does not cut the controller out and can still allow physical collaboration. A mixed reality headset such as Microsoft HoloLens 2 is a pioneering system that incorporates a mixed reality experience within an untethered headset. So this is the reason we employ Microsoft HoloLens 2. Moreover, it is designed for industrial applications and supports several integrated hardware sensors as well, unlike typical virtual reality headsets that are more geared towards gaming environments. Now, we realize that MR systems like Microsoft HoloLens 2 can possibly provide a self-contained digital tower system to visualize only relevant information. So another advantage of using a system like this is that operators can aim to potentially replace massive spatial displays seen in remote digital towers, which may also lead to a reduction in operational costs as well. So with these possibilities in mind, this is another question that we ask ourselves. How can the interaction capabilities of such a platform like mixed reality be used to offer a natural and interactive experience for controllers? Can we alleviate the unfamiliarity that comes with a novel digital platform for air traffic control? Now, we have seen that most digital towers offer limited interactions, point and click, menu driven, but research shows that embodied, which means using one's own body as inputs, hand or eyes or whatever body part, and direct interactions rather than indirect point and click interactions are more intuitive than indirect interactions. We also see that controllers do perform ATC tasks more effectively when such systems incorporate changes that consider better interaction design. So keeping all this in mind, this research further considers how better visualization options and better interaction design can ease this digital transformation for air traffic controllers and help gain their acceptance in using such a novel platform, apart from the many other advantages that it offers. So this paper, in summary, proposes a mixed reality-based portable remote digital tower system that has embodied and multimodal interaction capabilities. I hope this makes a bit more sense to you than it did in the beginning now. So to do this, we basically developed a simulated 3D digital tower environment in mixed reality using Microsoft HoloLens 2. This serves as a proof of concept design to base our interaction design on for a preliminary assessment before we move on to a more mature version of such a system. We're just treading the waters right now. So we added several visual features from real-world air traffic control environments to be visualized in mixed reality, and we incorporated interactive capabilities to them. So specifically to aircraft, gates, and runways. Now, the picture you can see is a demonstration of a 3D application in mid-air, placed in a physical surrounding. This is what one sees inside the mixed reality headset when they put it on, with aircraft, gates, and a runway. So we added several visual features from real-world air traffic control environments. So this is the overview of such a system, and out of tower view from a remote digital tower is visualized in mixed reality. Virtually inside the HoloLens 2, like we saw in the previous picture. Key controller tasks are mapped to hand and eye gestures using a multimodal interaction design model, which I will go into detail later, which are then fused to form interaction gestures. Now, the visualization and interaction model are combined to form an interactive digital tower system in the mixed reality space. So this is the overall system concept. Let's dive a little bit deeper with an overview of the system design. Now let's see how the various hardware and software components of our system are connected. So for hardware, we use Microsoft HoloLens 2, which comes with several different embedded sensors that track human input. So this tracks, in particular for our system, eye gaze information and hand gesture information, which is then processed by the multimodal interaction model that we have designed. Now, for software, we primarily use Unity 3D and Mixed Reality Toolkit to develop our system. Unity 3D is a standard game engine that is well supported by Microsoft to develop 3D applications in mixed reality for Microsoft HoloLens 2, and MRTK, Mixed Reality Toolkit, is a software development kit that enables this in Unity and is also an official SDK given by Microsoft for developers of HoloLens applications. So thus, after developing our Unity 3D application, we can build it and deploy it to Microsoft HoloLens 2 as a standalone mixed reality application. In our application, we use a 3D model of the airport with interaction capabilities and a very minimal visual setup as a proof of concept that includes 1 terminal, 2 runways, taxiways, 2 gates, and 5 aircraft in different phases. Now, in a conventional digital tower setup, the out-of-tower view is physically placed above information displays and flight strips containing detailed flight information. So controllers have to physically switch between the 2 views to get all necessary information. We design a concept called billboards to alleviate this issue. Billboards are basically labels or flight tags like we see in other digital tower systems that contain aircraft information that attach themselves to the aircraft. Now, co-locating aircraft billboards with the relevant aircraft allows controllers to switch between information retrieval and visual inspection seamlessly. but to avoid visual clutter and information overlay overcrowding, we propose a solution to this. We propose a hierarchical model of representing flight data on billboards. So in this model, each aircraft billboard works at 2 levels of abstraction and is also activated by 2 different input modalities, that is embodied human input modalities. So the first level is basically a basic view, which is activated by just gazing at the aircraft that you intend to retrieve the information for. So basically, an eye gaze gesture activates the basic view of a billboard. So this basic view has very minimal information that ATCOs would want to see at a glance, like the call sign and whether it's an arriving or departing aircraft. The second level of abstraction is the detailed view, as you can see on top, that contains much more relevant information, but it has to be explicitly activated by hand gestures. In this case, an air tap, a mid-air hand gesture that is well supported in mixed reality headsets activates this detailed view of a billboard. So the detailed view contains different information for arriving and departing aircraft, and controllers can explicitly choose whether or not to display it when looking at a particular aircraft. Now, to design the interaction model, aircraft, runways, and gates were identified as interactive targets, and we decided to embed certain functionalities within them. So the functionalities were identified as key actions to be included that include viewing of the basic and detailed aircraft billboard like we've seen. Billboard is a tag that you saw in the previous slide. We can also see the route of an aircraft, distances between 2 aircrafts, flight on a runway, and flights approaching a gate. So you can see some examples in the pictures here, but I will show you a more detailed view of all the available information, interaction methods in a later slide. Now, when it comes to interaction, embodied interaction has usually been shown to be more intuitive than indirect interaction methods. So we want our digital tower system to have enhanced immersion to allow controllers to focus on the out-of-tower view without distractions from auxiliary menu-based interfaces. So without having to do point-and-click operations on menus. We don't want that coming in between controllers' day-to-day operations. So directly manipulating objects with a user's hand is a familiar embodied interaction gesture in most mobile devices and wearable devices today. And moreover, controllers are already very familiar with interacting with ATC systems by hand-based inputs. But in such a task critical environment, relying on hand gestures alone may induce fatigue. So additionally, with augmented information in an out-of-tower view, flight tags and billboards create visual clutter as well, which also decreases potentially the situation awareness of the controller. So to address these issues, we propose a novel information overlay technique that restricts relevant information using the controller's eye gaze. This would essentially leave their peripheral vision clear and free to process other important events. So in our system, eye tracking is used to localize a spatial context where relevant information is displayed only in the zone being gazed at by the controller's eye. So this provides gaze-aware information overlay. So these 2 inputs form the basis of our multimodal interaction model. So in this paper, we basically also introduce a multimodal interaction model that fuses eye gaze and hand gesture in a very natural model, in a model that almost resembles physical human interaction, if I may say so. It's called the where-what model. The user's eye gaze specifies the where. For example, the user looks at a particular aircraft, and the hand gesture specifies the what. So in this case, the hand gesture is an air tap. And for example, the user performs a hand gesture that means show detailed billboard. So the user looks at a particular aircraft to specify where, and the user also does an air tap to specify what action to take on that aircraft. So this leads to the defined task being show detailed billboard on the aircraft that I'm looking at right now. So this is an example of what our interactions look like and the affordances of our system that I will show shortly. This model was mapped to various interactive targets in our system, aircraft, runway, and gates. So controllers can use a combination of eye gaze and hand gestures to perform various actions, like you will see now. So to view an aircraft's basic billboard, the controller needs to only look at a particular aircraft. Now, performing a mid-air tap gesture, like I'd mentioned, it's called an air tap. While looking at the aircraft unlocks more information about that aircraft, such as a detailed billboard and route. Air tapping two aircraft simultaneously will show the distance between them. Air tapping on a gate or a runway will also highlight any flight that is approaching these gates and runways. Now, this is a summary of the various interactive affordances that we have in our system. Let's see how it all comes together in a very preliminary validation of the system. So this is a very early study, an assessment of this mixed reality system for general insights and feedback. So this is a proof of concept system. So we wanted to see if this is an acceptable form of air traffic control systems, potentially to be expanded in the future to a fully mature version. So this part of the study was facilitated in part by a collaboration with LFV Sweden and the expertise in human factors. So the aim of this initial assessment was to get initial feedback of controllers' perceived usefulness of the system as a viable augmentation of a remote digital tower system, and also to assess the effectiveness of the interactions in the system. Now, we had 3 experienced air traffic controllers as participants. Given the limited availability of controllers, we go with subjective methods of user evaluation. We employed a think aloud protocol during the experience, which was followed by a semi-structured post-experience interview. Now, after an initial briefing, participants were asked to explore the 3D airport simulation and its visual features, and then to interact with available targets to visualize information. Now, simultaneously, they were also required to follow a think aloud protocol where they verbalized their experiences as they went. So let's take a look at how this turned out.
Pallavi?
Yes.
Pardon the interruption. You have 5 minutes left to your presentation time.
Okay, I will speed it up. So the results of their responses have been very quite promising. A user perception interview asked about controllers' perceptions of system trust, confidence, and understanding. So understanding in this case is defined to be their perceived understanding of the system and how it works. Trust is defined to be the belief in the system to perform their tasks reliably and consistently. Confidence is defined as the ability of a system to offer functionalities and interactions that create a perception of reliability and transparency. Now, during this interview where they gave verbal ratings, they rated the system highly in terms of trust and confidence, but they found that they felt that they needed some additional training to be more confident in using it. Thus, the understanding part of it was a bit on the lower side. We also conducted a system usability survey via a structured interview based on the standard SUS questionnaire, where participants gave verbal ratings as opposed to Likert scale ratings. So the questions in SUS can be seen as addressing primarily the usability and learnability of the system. So usability refers to the ease of use of the system. Learnability refers to the amount of training necessary to overcome the unfamiliarity of a novel system. Now, we found that users rated usability of the system favorably. But it was very interesting to know the answer of this particular question on the subject of learnability. So one of the controllers talked about the role of familiarity with using new technology that would play in the system initially, that not all controllers would find it easy to navigate this novel MR platform. So this suggests that such a novel system would benefit from some amount of training to be given. So finally, a thematic analysis of their think aloud responses also reflected something similar, and they gave us very useful insights and feedback on improving the system, and we understood how it really added value to the controller's day-to-day operations. These responses were grouped into visuals, interactions, usability, and learnability. And while they all felt that the interactions certainly were useful and added value to the system, they also found that hand gesture interaction, which is an explicit interaction, takes some time to get used to. So they also said that some perhaps limited training might be given to controllers to get used to the system. So taking into account the various comments on learnability and usability, we thus form a few general guidelines with which the interaction design of a mature version of the system would align. Firstly, from the comments, we see that eye gaze interactions are easier than hand interactions for users because one is an automatic gesture and the other is explicit. So more commonly used interactive features such as billboards will be mapped to eye gestures. So this means hand gestures are reserved to assist eye gestures in less used operations like gate and runway interactions. And we also found that controller preferences for level of visual information vary. So controller specific interaction and visual customization capabilities have to be added from controller to controller. So in conclusion, to summarize, the key contributions of this paper are a visualization of air traffic in mixed reality, a multimodal interaction design model embedded in it, and a preliminary assessment of with controllers who perceive this system to be a promising and useful way to augment information on a screen. So the findings from this is being used to guide the design of a large-scale interactive mixed reality system in the future that displays live out-of-tower views from cameras depicted as streamed video feeds in mixed reality. Vision-based identification of interactive aircraft, runways, and gates can be added, and also will be accompanied by an improved multimodal interaction design. So in the long run, this research aims to develop a completely viable alternative to the present immersive digital tower environments with the use of mixed reality. We're a bit along the way already, and we hope to make it all the way to this goal very soon. So thank you. Thank you for listening to the presentation. Sorry if I ran a bit over the time, but thank you. Any questions?
Oh, you were fine, Pallavi. You managed to finish just on time, so thank you.
Okay, great.
Thank you for that. Yes, very interesting presentation, really interesting work.
Thank you.
I would like to invite all of you to post your questions. In the meantime, Pallavi, you do have one question that's posted. Is stereoscopic vision required to use the headset?
No, because stereoscopic vision is mainly reserved for virtual reality headsets. So in mixed reality, you don't, it is not an immersive environment. So you don't need stereoscopic vision. You only have parts of digital 3D model. So you can view them like you would view an AR experience on a mobile phone. So you don't really need stereoscopic vision.
Okay, thank you. I have a few questions.
Sure.
While you were running the study, Pallavi, can you comment, were folks generally confused about the hand gestures versus the eye gaze gestures real time? Did folks experience that? Was that part of the learning understanding issue, do you think?
So I think the fact that eye gestures were not something that they needed to think about because the system would automatically detect their eye gestures and then find out which aircraft they were looking at. But hand gestures was something they needed to do. And it takes some time to get used to doing mid-air gestures if you're not used to it, is what I found in other settings as well. So they didn't they couldn't find their bearings initially when they're strapped on the headset and sort of waving their hand about. So that took some time, and that caught them off guard in the beginning, even though we've given them like a trial run. So they suggested that, but over time we saw that they did become comfortable. So towards the end of the study, they were actually doing it pretty well. So yeah, so it probably takes a bit of time.
Okay, and you have a comment from the person who posted that question that this seems like a promising approach. So good. Again, while we're waiting for questions, I have some questions. Can you tell us more about the relatively low, 2 is not that low, but the relatively low understanding score? I mean, for example, in your actual usability questions, you had everybody say, I would imagine that most air traffic controllers would learn to use the system quickly.
Yeah.
So I'm just wondering if you notice something or if there's just inconsistency there.
So I think it also has to do with the experience of the air traffic controllers. We found that so one of the air traffic controllers was a former one who has been in air traffic for 25 years and was very familiar with the system as is. So he acknowledged that it takes a little bit of time to get used to these very new systems. So I think that was the difference in the understanding question that we saw. So again, I think a larger study would cover all these biases as well. So yeah.
Okay, thank you. And I see we have another question, but first I promised Claudio that we would give him a moment to jump in. Claudio, do you have a question?
Thank you very much. I really followed this presentation with high interest. The main reason is that I have been part of a 3D visualization of air traffic display some time ago. And I'm surprised that it has been conducted with a Swedish university, which is Linköping University, having their siège in Norrköping, which they are highly qualified 3D visualization software programmers. And I'm surprised LFV haven't worked with them because the results were very relevant. Number one, 3 air traffic controllers, I believe, is too low for testing. Having 25 years controller trying to test new technology, it's irrelevant. We have this famous word, do not try to teach old dogs new tricks. And I'm telling you why. Because the 3D visualization project, I've been a major part of it. We were testing here 16 instructors and 25 students. And every single instructor, they would have switched to the 2D immediately, while, okay, ab initio, they like to play with it, not because they learn anything about it, but they like to play with it. Of course, they need technical support, because an air traffic controller needs to have clear guidance what they need to do. Now, I have 2 questions. What do you do with handicapped people? We had a handicapped student whose brain was 100% operational, even 150% operational. He had affections on the hands, okay? His body from the half down was unoperational, but the rest, it was okay. That's the first question. If you want to answer me now.
So you're asking how a person like that would approach such a system? With hand gesture interaction?
How would handicapped people handle such a system? That's my question.
Okay, so I think the use of hand gestures would essentially, it's not a very disability-friendly approach to interactions, to be honest. But again, I think that can be mitigated by the use of other methods, such as head tracking. That is also another input modality available in HoloLens, as well as a bit more of eye tracking. And possibly in this very rare circumstance, probably voice commands can also be thought of.
Thank you very much. In ATC, when we talk about headset, we talk about speakers, not about anything else, but you talk about goggles, including speakers, which is fine for me. The question is the selection of these air traffic controllers. They have to pass a medical test, and people, they do need to pass an eye vision test where eyeglasses are a problem. Have you considered this issue when you develop an whatever headset, goggle system? Because I know when I was in Norrköping, okay, we were doing stereographic visualization of the traffic, but the glasses they were using, those were restrictive for implementing such a system. Did you consider the medical issue?
Yeah, so in HoloLens 2, they are actually quite usable for people with glasses as well. So they accommodate a wide range of users. So their headsets are very adjustable. So as even for the ATC headset in that context, that would also be, it could find a place. It can be put together simultaneously. So I don't think they would clash as such. And also they're quite accommodating for people with glasses because I've worn them, and I think yeah, the people who used it.
Yeah, that's a good answer. But my question was different. Medical restricts people with eyeglasses, with glasses in general. Okay, do not restrict them entirely, but they have lots of restrictions. Now you put more glasses on their vision. Have you considered that from a medical and certification? Thank you.
Okay, so I think a solution to that would be the transient nature of the glasses. So you can lift the visor up and down, and it is also it is, as far as the controller's initial feedback said, it did not impede their vision in any way. So I would assume that would be correct, but of course we have to do a larger scale study to form the to form conclusions about that.
Thank you.
Thank you. Pallavi, we have one more question, if you could be brief, and I think you can. The question is that, first of all, a comment, very interesting study. I wonder if you have ATC participants who could be novice versus experts, and that may be affecting your familiarity question that you uncovered as a challenge.
Yeah. So I think we already talked about this. So we did have one participant who was more experienced, but I don't think I have time, but they did have very interesting comments versus the people who were considered novice ATC controllers. So he was very accepting of this technology as such. He just didn't know how to use it properly. But as such, there was I think he was more readily accepting and less critical of the system than the novice controllers were, because they're very familiar with technology and they know its limitations. Yeah.
Right. All right. Thank you, Pallavi. We've come to the end of our time. Great job. Thank you. Interesting work.
Thank you so much, Sandy.
Yes, thank you, Pallavi. Exciting work. We virtually applaud for you again.
Thank you.
All right. We have our last presentation, certainly last but not least. Professor Hartmut Helmke has a diploma degree in computer science and a doctorate degree in chemical engineering. He has been with DLR, the German Aerospace Center, since 1989. And since 2011, he has been leading several international speech recognition projects, many of which have been actually presented at ATM seminars in the past. He has been leading several international speech recognition projects, including the Cesar-funded Hawaii project, which is the subject of this presentation. Hartmut, over to you, and thank you.
Thank you very much, Sandy, for this kind introduction. And yeah, as again, always good afternoon, good morning, good evening. So I'm the last, maybe, until you can go to bed. I do not mention all my 13 co-authors and also not all our partners. So what I want to talk about today is really about readback error detection. So yeah, you see here an utterance of a controller, and you see here the reply of the pilot. Yeah, and well, you immediately have to decide if is it a correct readback or is it not a correct readback. Yeah, and I want to give some hints on how a computer can do that. So what I in detail would do, I present some use cases with respect to readback error detection. I will tell a little bit what is a readback error and maybe what is not a readback error. And I want to also have a little bit interaction with you when we are talking about requirements with respect to, for example, false alarm rates, which immediately then results in plausibility measures. And of course, at the end, I hope I have some conclusions. So I must admit that is just ongoing work for our readback error detection assistant, but I hope that in all of the chapters I can present already some of the results we have. So here you see maybe a very complicated overview. It should just show what use cases are there, though. Now, the communication could be, of course, initiated by the pilot, or it could be initiated by the ATCO. There could be a correct readback by the ATCO, or there's a wrong readback, which is corrected or which is not corrected, and so on and so on. So it's not just a simple case of the use cases. And involving more ATCOs or more pilots, it makes it even more complicated. So let's just look at an example. The pilot starts the pilot starts the communication. The ATCO wants just a descent to flight level 310. The pilot's answer descending 310 is here correct. So the system's answer, of course, should be indicating no readback error. In this case, well, the ATCO starts the communication descending at 250. The pilot's answer is then descending to 210. Yeah, I think it's clear. This is a readback error which should be indicated. And if there is no reaction of the ATCO to this readback error, well, then we call this a hearback error. And well, but if the ATCO is acting maybe really was negative and then repeating descending 250, yeah, then we have no hearback error. It's just a correction, and we hope then that the pilot in this time correctly repeats the right altitude, and then we expect that the readback error indication disappears. Now, here use case which you also should not forget, there is an ATCO command, but just there is after some time no pilot readback. Yeah, then we have a missing readback, and we should have an indicator for the ATCO to remind him that there's still a readback missing. Here we have a more complicated use case, which involves not just one pilot, but more pilots. So, well, the ATCO says turn left. The pilot's answers is turn right. Yeah, and maybe, yeah, this is a readback error for this call sign. Yeah, and if then the ATCO is talking immediately to the next call sign, well, then we have a hearback error. At least the system should indicate a hearback error for the first pilot. Yeah, and then if the second pilot is then answering and making a correct readback, well, for the second aircraft we have then no readback, but still for the first aircraft the hearback error remains. Yeah, and then let's hope that the pilot then corrects the readback and before before the ATCO gives the command again to turn left. So, and then the pilot hopefully will correct it, that he says then turn left. Well, then of course we expect that the readback error indicator disappears. So yeah, you have seen that it is not so simple. Yeah, just having one use cases. Many use cases here really exist, which needs to be considered by a readback error assistance system. But it's even more complicated. Yeah, what's really a readback error? Not just the simple use cases. Yeah, just have a look on the simple case. The ATCO says something the pilot is repeating. Yeah.
Viewing 2 Delta Zulu, descent from level 70.
Well, this we want to do this by speech recognition, of course. And well, what the speech recognizer has to recognize here was just a ruling 2 Delta Zulu and so on. And here we have the readback of the pilot.
Descent is level 70, well into Delta Zulu.
It was understandable, maybe at least if you're listening several times, but the speech recognizer has only one chance. This was what the pilot has said. Well, and in this case, it's easy. It was correct readback. But yeah, now have a look again on my initial motivating example. Now, there the ATCO has said, good morning, Speedbird 200 Alpha. Reduce 180 knots until DME 4 miles. Contact tower on frequency 118.700. And the pilot answers might be 180 to DME 4, tower 187, Speedbird 2000 Alpha. Yeah, I think you immediately see already it's not so easy to decide looking on the words. Yeah, and it's even more complicated when a speech recognizer tries to understand all the words. Yeah, so what is it a readback error? Well, you have seen maybe that the sequence of words which the pilot and the ATCO are using may be completely different. And that's real life. Yeah. And not each command which is given by the ATCO needs a readback. And the sequence in which the pilot is doing the readback must not be identical to the sequence of commands which the ATCO has given. And you also might have seen the pilot says 19. The ATCO has said 119er, and the other has said 1000, the other 000. So we do not want to discuss about phraseology here. Is it good phraseology or not? We just want to decide, is it a readback error or not? Yeah. And yeah, what this also should show, yeah, what Alan Turing already has said 69 years before. Speech recognition, yeah, just recognizing the words is completely different from speech understanding. Yeah, though an ATCO might have no problems. Yeah, Claudio, I think you will understand what that means, but there are many in the audience here have really problems to understand that, and it's not a readback error here in this case. So, and well, how can we now do the speech understanding? Yeah, and here really the CESAR funded project 1604, which ended 3 years ago, really helps here, because here 22 European partners agreed on a so-called ontology, yeah, rules, how we want to transform controller words and pilot words into simpler representation. So how to do the semantic interpretation. Yeah. And we agreed on that a controller or pilot utterance consists of one or more instructions, and each instructions consists of a call sign, a command, and maybe optional conditions. And the command itself, well, it consists of a type, always, values may follow, and optional are units and qualifiers. And maybe you also have a reason which says that it's a readback or that's a request or something like that. So let me give an example. Yeah, this utterance with this rules is transformed into the call sign. Here you have the type, here you have the value, here you have the unit, and you have also, in this case, a condition. Yeah, and so on for the second command the controller has given, and the third one here in this utterance. And if you are doing that also for the pilot, yeah, although the words are completely different, now it's very easy. Yeah, here nearly you have the same strings. Yeah, it's just a string matching to decide whether you have a readback error or not. Yeah, and though this agreement by the 22 partners, European partners, really helps to ease readback error detection, although it was designed for very different applications. So let's have a look again. There we have here what the ATCO says. He says something direct to whiskey 982, and here we have a readback. The pilot says whiskey 972. Yeah, difficult to decide, but looking here onto in the ontology, yeah, you have here whiskey 982, and you have here whiskey 972. Yeah, now it's easy to decide it's a readback error. More complicated now. Yeah, I really want to integrate you now a little bit, or what is the audience thinking? Yeah, here you have, well, I just go already immediately to the ontology. Yeah, here it was a change by the ATCO, change to 124980. Yeah, but the readback of the pilot is 124900. Is that a readback? Is that yeah, of course it's a readback, but is it a readback error? No discussion about the phraseology. Just yeah, is it a readback error or not? Yeah, and if you're really now encouraging people, or I really ask you, can you use the chat? Just type in yes, no, not sure. Yeah, so yeah, I'm talking all the time. Maybe you can also do something here now. That would be just fair. And there's somebody from all my co-authors maybe collect these answers. So we did the same during a Hawaii workshop. You can see here, you can download the results from the Hawaii homepage. We asked 40 participants, really experienced people in that area who just participated in this workshop for readback error detection. Well, and most of the people said, well, yeah, it's a readback error, but some have doubts and some say, no, I don't know what, in some cases maybe, but in some cases it's not a readback error. So you see, it's maybe not so easy to decide if it's a readback error or not. Here again, another thing. Yeah, I just immediately go to the ontology, yeah, here in the readback, the ATCO says the call sign, but the readback of the pilot does not contain the call sign. And again, to the question to the audience, you can again use the chat, maybe type Q2 for the second question, and then yes, no, or not sure, or something like that. Is it a readback error? What do you think? Yeah, and well, interesting was really the output of this workshop with 40 people. Yeah, the same amount of people say it's a readback error as the same amount of people say no, it's not a readback error. And but there were also some people who said, well, I'm not sure. So the majority of the people could not agree on is it a readback error or not. Yeah, though, is it necessary to provide the call sign? Well, with a little bit more information, look into example of utterances. Here's some of my results. We have looked at the utterances of one ANSP, and we have seen 15% of the utterances of the ATCO are not containing the call sign. Not that the speech recognizer is not able to understand it. No, they are not there. And 90% of the pilot utterance is not. Yeah, and for the other ANSPs, yeah, we get similar results. And you see also, well, if you have a sloppy ATCO, you also have a sloppy pilot. So there is more or less a correlation. But this should just show if you address that it should be a readback error, if the call sign is not said, well, then you have 50% of readback errors, or maybe during the conversation. So I think a call sign does not need to be said, although according to the book, it must. Yeah, we have the same results, a little bit more data from a previous project, which ended 2016. There we only had data from ATCOs. And here for Prague, well, 10% of the utterances do not contain the call sign. And well, if you think you can do the same in the operational environment, really from real data, then you can do in the lab with speech recognition. Well, I would say then you're wrong, because these numbers really show in the lab environment, the ATCOs in most cases are using the call sign, and or well, Vienna controllers even nearly always are using in the lab environment using the call sign, though. Yeah, there is really a significant difference between lab and ops room environment if you're talking about speech recognizer. So we need to go to the ops room. Now, if you're looking onto units, if the unit is used, yeah, well, here you have an utterance where the ATCO uses the unit and the pilot is not using the unit. Yeah, same question. If you want to type yes, no, or not sure, yeah, do it. And well, if you see here the feedback from the Hawaii workshop, well, most of the people say no, it's not a readback error. The unit must not be provided, or it's not needed that it's provided. So if you're looking at the data which we have, well, you immediately see, well, for the ANSPs, for the ATCOs, in most cases, the ATCO is providing the unit, but the pilot is more free in his what he reads in the book using the phraseology. So our results from the workshop were really you have to decide readback errors which are according to the book, readback errors which should be brought to the controller's attention, and third, readback errors which should be really communicated with the pilot. Well, that's a difference. That are the severe ones. So let's talk a little bit about requirements. Yeah, our requirements in the Hawaii project were we want to detect more than 50% of the readback errors. Now that means 51 of 100 readback errors. Our false, this is not very challenging, but the false alarm rate should be below 10%, which means if we have 100 alarms from the system, 90 should be correct. That is really, really challenging, because readback errors in real life are really seldom events. They are not very, very seldom events, but they are seldom events. So we expect 2% of the utterances only contain readback errors, and most of them are corrected. So what does it mean now that a readback error is detected? Well, a readback error is then detected if the utterance of the pilot is correctly recognized and the utterances of the ATCO and of the pilot are correctly recognized both. Yeah, that means the call sign must be correctly recognized, the type must be recognized, the value, the unit, and so on. So everything must be recognized. Yeah. correctly recognized. So that means if you have a recognition rate for the ATCO utterances of R, ATCO, and of this for the pilot, well, it's just the product of both probabilities that the recognition is correct. Yeah, with some simplification, yeah, yeah, with the simplification that they assume to be independent, you can do the simplification. So then you can say that the readback error detection rate, yeah, is really the product of the both recognition rates. So, but you see that the readback error detection rate is really independent of the rate how many readback errors you have. Though if we are looking on some data here with the formula, well, in the Mallorca project, we really had in the ops room on the ATCO side a recognition rate of a complete command of 92%, which is really, really good. We did not measure for the pilot, but let's assume that we have 85% for the pilot. So then our readback detection rate would be, with the data of the Mallorca project, 78%. Let's look on the more challenging part on the readback error false alarm. Yeah, don't look here on the formula. It's more that you see here that here the readback error rate is really depending on the frequency, how often you have a readback error. So if you have 5% of readback errors, the false alarm rate will be lower than if you have only 1% of readback errors in your environment. Or if you're using the Mallorca data, you will get here, yeah, that with the really good recognition rate in the Mallorca project, yeah, you will have still 62% of false alarm rates, yeah, and here, yeah, we consider really the error rate, yeah, and you have an error, you have a false alarm if the pilot command or the ATCO command is wrongly detected and it is not rejected by the speech recognizer. Yeah, 62% sounds a little bit much because the requirement was 10. But yeah, think about if you have 1,000 ATCO pilot pairs, yeah, then we have 20 readback errors, yeah, assuming 2%. So then with this rate, 15 would be correctly detected, yeah, 5 are undetected. And well, we have still 24 false alarms, yeah, which sounds a lot. Yeah, but also keep in mind with this rate, more than 950 ATCO pilot pairs are really correctly recognized and determined that there should be no warning. So, but here you see really are the main meat here of the output. Here you see in the cells the false alarm rate, yeah, the false alarm rate which we have. And well, here you see the recognition rate for that both the ATCO and the pilot commands are correctly recognized. And here you see the error rate, yeah, which means that at least the ATCO command is wrongly recognized or that the pilot command is wrongly recognized. Yeah, and so you see, well, for the false alarm rate, the recognition rate is not really the challenge. Even with 50%, you might achieve a false alarm rate below 10%. But the error rate, yeah, is really, really, really challenging. You see, well, that if you really want below 10% of false alarm rate, you need an error rate below 0.2%. So from 1,000 ATCO pilot pairs, there only 2 are allowed to be wrongly recognized if you want to achieve this. Yeah. So you really need to be extremely good. Yeah, and well, we are considering, yeah, we have recognitions, you have errors, and yeah, the trick is of course that you also can have rejection. So if this recognizer is not absolutely sure, he said, well, I'm not sure, no output. Yeah, I forget my opinion though. That's a chance. Yeah, so that's the sum of the recognition rate and the error rate is not 100% because you have the rejections. So that means we need something plausibility measures, yeah, that the system can say, well, I'm not sure, better no output. So in plausibility measures, yeah, how we can get that. And here I have an utterance, try to listen to it.
Level 110 is 110.
Yeah, So this might be a hint here. Maybe, yeah, you have understood nothing. I have understood nothing. So here what was said was this.
Number 110 is 110.
Now here two pilots are talking at the same time. That's a problem. Though in those cases, maybe, yeah, there should be an output, an indicator, which shows that yeah, we have low plausibility here. Yeah, and well, this utterance maybe should be excluded from readback error detection. Surprisingly, this was nearly perfectly recognized by our speech recognition system. You have another utterance.
Action 5, Quebec Juliet, descend altitude 4,000 feet, be level by Avata.
Yeah, that was the ATCO. I think, yeah, with some training, easy to understand. But nevertheless, here the output of the speech recognizer was something like that. Be leveled by at air, sir. Yeah, a little bit nonsense. Though really was said, be leveled by the waypoint Iwata. Yeah, though how to give plausibility measures that we are not really sure, yeah, with that. Though our trick here is, well, we are looking on the output of the speech recognizer and we are classifying each word. Yeah, for the 1,000, we are classifying it could be a value. For the feet, we are classifying it could be a unit. And then with this here, with this long term, well, our speech recognition output is not unknown. Yeah. And if we have a lot of unknowns in the classification, yeah, then we say, okay, reduce the plausibility. Though that's one of the tricks we want to use. So here, this example shows some good news.
28 Tango X-ray, contact Lambda radar 134.355.
So this was really the output of the speech recognizer, but really said was 428 Tango, or at least we believe that the ATCO has said that, and but both is wrong. Yeah, what was understood by the speech recognizer, but also what we thought was thought. So really, I think the ATCO wanted to say November 428 because only in November 428 is in the radar data. So we expect here that the November was blocked out by pressing too late the push to talk signal. But yeah, luckily, well, what we call assistant-based speech recognition already for a long time, using also the information from the surveillance data or output from an assistant system will immediately help to reduce this ambiguity. Because, yeah, well, we know from the surveillance data that only in November 428 Tango X-ray is in the radar data. So this is the nearest match to that, and this is also the nearest match to that. So this helps really to reduce error rates. Yeah, and here you have some data with respect to that. So we have used surveillance data, yeah, and then we get extraction rates of 99%, recognition rate on command level. The error rate is very low, still not what we need. Yeah, but if we are excluding, if we are not using the surveillance data, yeah, immediately the call sign recognition rate already goes dramatically down. Yeah, and we have the same data here for other ANSPs. Yeah, if we are looking on not only on the call sign recognition rate, but the recognition of the whole command, yeah, with using the surveillance data, yeah, we are nearly perfect. Without it drops again. Yeah, and you have the same results here for the other ANSPs. But okay, the data which I have just presented you was a little bit cheating because the input for the extraction algorithm was the perfect human transcription. And yeah, it even for the perfect human transcription, though manually written down all the words which are correct, the extraction algorithm is not perfect. But yeah, the challenge is for this semantic interpretation algorithm, it must be able to handle the output of a speech recognizer. And you know, not all the words are correct. So we are happy if we have only a word error rate of 7%. And for pilots, I think we need to accept 10% of word error rate. But with this, at the moment, well, using surveillance data, the call sign recognition rate is 95%. Without on real data, well, we have 79 only, and we get the same here for the other ANSPs. If you're looking on recognition of the whole command, okay, yeah, you see we are in the middle of the project. We still have to do something. So that are the numbers from March when we have written the paper. Only a little bit better, but still we are not perfect. Though, but the message should here be, yeah, you must consider surveillance data. Otherwise, you will not get the rates, and they are available. So use it. Yeah, let me come to my conclusions. So I think it should be clear from this presentation that if you want to create a readback error detection assistant with radar, well, you do not have only the one use case, yeah, where the ATCO is saying something and the readback of the pilot is correct or wrong. Yeah, also you have missing readbacks. You have to include more than one pilot, or the pilot could make a request which is completely nonsense, or in the current situation. Yeah, that everything that a readback error detection assistant must support. And well, I don't know if you have used the chat now. I have no chance to look into it, but I think there is still no common agreement concerning what is really a readback error, or say it better, according to the book, maybe, yeah, it's clear. But what is interesting really for the ATCO, and what is then should be really also reported to the pilot, yeah, that are really 2 or 3 different things which we need to distinguish, and maybe then we can come to common agreements. Well, we have extended this ontology, the rules for transcription, for annotation, the writing down the semantics, and I have shown, I hope, that with this, readback error detection is easy. No, not easy. It's a little bit easier than before. Yeah, so because it can be reduced to just string matching. And well, really challenging is the false alarm rate of below 10%, which because it requires that the error rate must be below 0.2%. Yeah, the trick is here maybe that you have a lot of rejections. Yeah, but nevertheless, the command recognition rate should be above 90%. So, and the trick are really here plausibility measures. And what we are currently also thinking about, to get this low number, let's use redundant readback error detection engines and different speech recognizers. Yeah, and only if all of them say, well, yeah, here's a readback error, then show it to the ATCO. And I think what I have shown, and also in other talks already, yeah, use the surveillance data. Yeah, otherwise you will not be able to get these low error rates. So the final remark, I think readback error detection is really the king discipline of speech recognition applications in ATM. Yeah, and remember maybe a talk of JFK 60 years before. Yeah, he said by the end of the decade, we will be able to install a readback error detection system in the ops room. We are not going to the moon until the end of the decade, but that's our challenge. And yeah, I hope that I have a little bit encouraged you. I think we can be able to do that together. Yeah, but not one company alone, but yeah, let's address it now. Thank you very much for your attention.
Thank you, Hartmut. As always, a very interesting talk, and thank you for your continued contributions to this field. We do have one question. I would like to ask a question, and it's maybe more a comment to invite you to comment on as well. I think that the issue possibly with readback errors is in the case, for example, of using a metric or not. A concern about dropping the metric is that there are obviously some operational environments where the aircraft is operating, and 180 could be knots or could be heading, or in some environments could even be something else. So it's more a confirmation to use the metric, and that's why the metric might be particularly important in some operational environments than others. So I don't know if you agree with that, and if you do, is there any way to address providing context around something when you define that it's an operational error?
Yeah, well, I think without context, you're lost. Yeah, that's we are also using context now. Yeah, otherwise you would not be able to understand what I'm saying, or you are still not even able to understand each of the words which I'm now saying. Yeah, and but you have a lot of context information, so that your brain maybe is able to derive what I could a little bit mean. Though that's what we also have done, and which I have shown. You need to include the radar data. Yeah, though which call signs are in the air. And the call sign is mostly set in the beginning. And though if the pilot starts talking, well, he might be surprised by the first words, but with all the context information that he knows that is in Austrian 6904 in the air, yeah, he is able to do that. The same is what you have said, 200. Yeah, if the readback of the is thank you 200. Yeah, that often happens. Yeah, what does it mean? I know the Airbus 200, or is it a heading 200, or is it a altitude 200? Well, yeah, you need to include the command of the ATCO. Otherwise, you have 2,000 readback errors. Yeah, of course you can say, well, according to the book, it's forbidden that a pilot is saying that. Yeah, but that's clear. Yeah, but I think we are now long enough in the business that what is according to the book and what is forbidden and what is real life. Yeah, so and also our task should not be to educate controllers with a speech recognizer. Our task should be to help them.
Okay, thank you.
Long answer for a short question.
That's okay. You do have a question. I know Claudia also wants to ask a question, but let's start with the one in the Q&A. What other speech recognition applications in the ATM environment do you see for the near future?
Oh, yeah, good question. Though, not really, or not only having, not only wanting to have the readback error detection, or that maybe was the answer with respect to John F. Kennedy. Yeah, that I want to only have it at the end of the decade. Yeah. Well, I think all the applications which are not forced to directly go into the ops room. Yeah, we can do already now. I think that's for example, something what the US guys are doing, yeah, at MITRE. Yeah, that they already have every month 130,000 hours of data where they are just analyzing how often a CDA approach is given, how often heading command is given. Though with that, I think you are not forced to have 90% of recognition rate. You just want to know the average. So if you have 70%, it doesn't really matter. Yeah, though I think there's applications you can immediately implement, and there are no safety issues. Yeah, at the moment you get data which you at the moment do not have. Maybe data privacy issues, maybe an issue. Yeah, which might be solved, but not a safety issue with respect to that. If you want to go to the ops room, yeah, of course, I think highlighting, not highlighting, pre-filling in the radar labels, yeah, not doing every input with mouse or with keyboard. That could be applications which I'm really seeing which are ready for implementation already now. Yeah, and of course, if you want to replace your pseudopilots, yeah, because then you can always say, if the speech recognizer is wrong, then you're a bad controller, because that's for the trainees. Yeah, I think that you immediate applications, I would say. I hope that answers the question.
Yeah, thank you, Hartmut. And Claudio has his hand up.
Yeah, well, I cannot write a question in the Q&A because although I'm a host, I do not have the privileges. This is the beauty of virtual environment. I think what you are talking about is the never-ending story of the call signs true, 3, and 141414, which we use very often in ATC training to train the controllers to avoid this thing. I would call instruction, a control instruction rather than command. But I have a thing. I remember several years ago, certain pilots were not allowed to fly in certain areas of the world unless they would not have had an ICAO level 4 English recognition, because their English language was so bad that they would have increased the control center's workload. I don't want to call it towers, approaches, or ACCs, but their English command was so bad that effectively they would have increased by 70% the workload. Did you consider these different accents when we talk about voice recognitions?
Yes, yeah. But on the pilot side, you see our recognition rate on the pilot. So we have data from different areas in the world, and also Chinese pilots or American pilots with all their different accents, but that you do not have in mind, I think, Claudio, yeah, with the bad English, also Germans or Spanish. We have included that, but you need training data. Yeah, if you have a speech recognizer which never has seen a Romanian controller, it will have a problem. Okay, you might say then the Serbian controller has nearly the same accent. Yeah, that's okay. Yeah, but if you have Chinese and you have never seen somebody from the Asian environment, you will have a problem. And maybe speech recognition is your solution. Yeah, that no controller will understand the Chinese guy, maybe. Yeah, but the speech recognizer is trained to that, and he understands it. Of course, it's a safety issue. Yeah. So yeah, we have considered it.
Thank you very much.
Okay, Hartmut, I don't see any other questions, but I think we have time for one more. So I have one. Can you please explain the usefulness of this technology as we see continued development and usage of controller pilot data link?
Oh, I know, yeah, always this question. Yeah, we have the controller pilot data link, and now forget the speech recognition. Yeah, that's always do we really have controller pilot data link, or do we really have it only in theory, and we have it on all the conferences, or is it really running in operation? That's my first answer. The second answer is, well, one of our partners is ESAVIA from Iceland. They really have 70% of the commands are exchanged via CPL DLC. And they are the guys who are interested in the readback error detection assistant, because they also want to address the other 30%. Yeah, though, and we will never have, maybe, yeah, but I think not during the next ATM seminars, or only 5% communicated via voice, and the rest via CPL-DSC. So for that, we need, I think, speech recognition. But yeah, readback error detection is only one application. Yeah. Should I now answer everything via typing in something? I think voice is one of the most efficient communication means which invented by human mankind. It's maybe a little bit not so redundant or so safe, but I hope that you want to talk with me here with voice and not writing everything. Yeah, though that's one part of the other. And another thing is, well, even with CPL-DSC, where does the input come from the ATCO? Is it coming from mouse or from keyboard or from touchpads? Well, it could also come from voice. Yeah, that the voice with voice recognition, the controller makes the input, which is also another, maybe to Claudio for before. Yeah, why teaching the controllers to using different means? I hope all the controllers are able to speak. Well, most of them. No, I think they must speak. Speaking, they must be able to. Otherwise, we have still voice communication. And think about of Google and Alexa also. Yeah, do you think that they are throw out all the speech recognition things? I think they have the reasons why they have invented it. So, Sandy, I hope you are satisfied. No, you're not satisfied, yes. But you have to accept my answer.
Yes, yes. Thank you, Hartmut. And thank you again for your presentation and your work. Virtual applause for you. And we have come to the end of our time. So a virtual applause for all of the folks who are our speakers. This was a really interesting session, and also virtual applause for everybody who was in the audience. It was a very engaging talk. So thank you all very much. Please take a moment to join the wrap up for the day. And don't forget that is the link that you got when you originally registered for the conference. And please don't forget to join us for tomorrow, the closing day, with interesting talks, including a talk on COVID in the US and the Best Paper Awards. So that concludes our session. Thank you again for everybody for your participation.
Thank you very much, everybody.
Thank you. And thank you, Claudio. Yes, thank you.
Helmut, I might get back on you sometimes on the email.
Yeah, please do that, Claudia. Yeah, I think
talking about the CPDLC. The CPDLC is still monitored by the voice correction, so it's not yet in place to replace the RT. So
yeah, well,
that's a lot of challenge with CPDLC. Yes,
there's a lot of challenge, yeah, but although I think for a long time we will have voice. But Claudio, let's just go to the other one, and let's keep in touch. I know you are a controller.
Thank you very much.
Bye.
Thank you. Bye. Bye.